Oh, you is working. Somehow working. Okay. Then where? Let's see. Yeah. Type your name. Okay. Okay, I can send you even the WeChat. Is it working? It doesn't make a presentation.
So sorry. Well,
Okay, there's some presentation mode. Wonderful. And can you show the PDF file? And the full screen? Oh, wonderful. Okay, so your laptop is, this one is working, so my laptop is clearly working. Okay, anyway, so I found that this is very useful. So star is the source of star energy in star is a thermonuclear reaction, and all pressure is radiation should be taken into account the equation for equilibrium. So this is what Eddington did. So after the like a heavy star, like a whatever 20 solar mass and so on, as the star gets old, the core of the star become like this will become rare. So the in the middle you have iron and silicon, magnesium and neon. And neon and so on, those are the layer of the stars. The star gets old, and then anyway, so then you have a let's see. So as you finish the nuclear reaction, so the gravitational collapsion will win, so that the contraction will occur, and if the star is less than radius, less than the mass is less than 8 solar mass, and so on, it becomes the white dwarf, and then so the Chandrasekhar found his famous limit to support this gravitational, I would say, collapse versus electron degeneracy forces. That's 1.4 solar mass. Okay, and then so there are lots of things going on. So some star become the neutron star, and inside a neutron star also is believed to have this kind of layer. So superfragile neutron superconducting for proton. There's a proton inside, but the surface you have a superfragile neutron and then some crust for in the neutron star. And here's the how the star gets old. So start with some main sequence of star per star, and if the mass is less than the 8 solar mass, as I said, this is solar mass, and it becomes like a giant, it is a giant, and then you have a helium splash and so on. And as since the gravitational collapse, once gravitational star collapse happens, so that the outer layer will be this flashed. So that it becomes the layer becomes nebula. How to say in Chinese? Do you know? Anyway, so and after that it becomes the white dwarf. And if the mass of star becomes large enough, it becomes supergiants. And then again, once gravitational collapse occurs, then undergoes, the star undergoes supernova. It's called type 2 supernova. And then some of the, if the star is big enough, it becomes black hole, and there's some less than 20 solar mass and so on, 40, less than 40 solar mass and so on, it becomes neutron stars. Okay, so those are the, can you see clearly? Anyway, so those are again the how the star gets old. I mean, of course, the lower the star is, the mass lighter. Lower the figure, lower figure is the lighter star, and then I mean, anyway, so it's hard to see here. Anyway, so those are the how it grows, how the star grows. Hopefully, yeah, type 2 supernova, and around here it becomes all black holes. So fine. Okay, so then there's a story about supernova, but I'm not gonna go into the detail. And then once so those are already, yeah, I mean, nowadays more than half a century passed, yeah, after the Einstein theory, the birth of the general relativity. But the concept, as I mentioned, concept of black hole is a big idea. And then first Oppenheimer and Snyder mentioned that there's if the star is big enough, the gravitational collapse is unstoppable. Okay, so that's 1939. And then before that, a few months later, or a few months after the birth of GR, Schwarzschild found one exact solution. Here, it's kind of an amazing letter from Schwarzschild to Einstein. One of the, he was at the, anyway, so the Russian front in the World War I, I think. And then he found the opportunity to deduce the first exact solution Einstein field equation. As you see, the war is friendly to me here, right? But unfortunately, he passed away during the war. So anyway, so those are kind of like a story of the Schwarzschild. So he did even like a computation during the war. Okay. And then so here's what the Schwarzschild wrote. The paper of the Schwarzschild R mu nu equal to 0, and they have a spherical symmetry, and so he derived this his famous solution. And if you solve it, you will get this the Schwarzschild radius and so on. Okay, so that's what he derived. So the Schwarzschild radius is the 2 times gm over c squared. And then apparently the metric somehow becomes the singular, and the question is the what's happening at the radius, this or event horizon. And then after the Finkelstein appeared, this is the causal structure of the Schwarzschild black hole. So again, as I mentioned, r equal to 0 is the singular position of the singularity, and the event horizon is the Schwarzschild radius. And then causal structure, as you can easily see that the older cone is the inside once you enter the just 2 words the singularity. So that once you enter the singularity event horizon, you have to your fate is destined to move toward the singularity. Okay. So that's how the causal structure look like. And then we introduce so-called tortoise. It's called let me write it down. So it's called. So this R star is called coordinate. So towards is the in Chinese 五归, because I mean it takes infinite time from infinity to the short radius if you use this coordinate. I mean, if you integrate out infinity to the r, so it takes like really infinite time to go to this. If you use this, oh sorry. Anyway, so once you introduce this torus coordinate, then the metric becomes the non-singular the event horizon. So let's go adding the Finkelstein coordinate, and then causal structure look like this. Somehow there is some anyway, something strange, but here is the singularity, and this is the event horizon, the location event horizon, and the light cone always towards the singularity once you enter the event horizon. Fine. So then, so if you start with the past infinity and the star which start collapsing, so this is the shape of star, and this is time direction, and then once the star collapses to the singularity, it just create this like a line of the warp line of singularity, and then there's also a warp line of the particles, and as you can see, light cones inside. So this is, I think, what Penrose has drawn. I think. Oh, sorry. I think I'm moving backwards. Okay, so those are causal structure. As you can see, so this the combination of the curvature, you get the 1 over r squared, and so on. Fine. Birkhoff theorem I will explain. So since to derive Schwarzschild radius, Schwarzschild metric, we assume that it is static, so the metric is independent of t, and it's spherical and so on, spherical and so on. But Birkhoff theorem, we will see that so our assumption is like without static we can derive Schwarzschild metric. So that's the Birkhoff theorem. So you only assume that the metric is spherical symmetric and the vacuum equation, and then you can derive the Schwarzschild radius. That is called the Birkhoff theorem. Okay, so that's what we're going to see. So we don't need to go into the detail. I think those are what we are going to see from the coming lectures. And these are the Carter-Penrose diagram, or whatever you call it. So those are the Penrose diagram or component diagram for the flat space, as I explained last time. Yeah, so then you can just always somehow scale by component factor. But since we use the B's constant, U's constant is actually the light ray, so the causal structure will be preserved. Okay. So those are the Minkowski flat spacetime. It's very easy to see. So that so this vertical curve is the what's that? R equals to constant limit, or x equals constant limit. It's just t varies, and then the horizontal curve is the t is equal to constant curve, like this way. Okay, and this is the Penrose diagram for the Schwarzschild black hole. So in last time we only looked at the last I draw this kind of diagram. So this is called eternal black hole. Eternal black hole means that we don't assume the collapse of the star. So therefore there is a white hole and black hole, and then causal structure becomes like this way. But for reality, black hole is believed to be created by collapse of star. So this region will be gone. So this region and this will be gone. and then you have to start with some whatever spherical star. So this yellow part is a star, and then it just undergoes a gravitational collapse, and then collapse, and then it just hits singularity, and it creates event horizon. So this is the real Penrose diagram, real black hole. But here it's just a short shield, so it's anyway. So these are eternal black hole, as I wrote here, and then so it's not it's just a theoretical one. Okay, again the other coordinate of the anyway. So those are the, and we introduce classical Zecharis coordinate. Sorry, I don't know how to pronounce his name. Zecharis coordinate, and then if you use this one, you can just see that the space-time becomes flat up to some conformal factor, and so on. Okay, so that if you use this coordinate, the structure becomes that we already see. White hole for in the eternal short space-time, we can introduce white hole whose constant structure become like this way. Okay, so this is black hole. So the timeline, and it becomes singularity. But here you have a singularity and the symmetry axis. Okay, and everything moves towards the outside. Okay. I think that's what I wanted to show, and this slide is actually very good, so I don't need to do anything actually. Anyway, so those are we are going to learn from the subsequent lectures. Anyway, the Chador equation and so on, or even singularity theorem we will see later. Killing horizon we will introduce the notion. I think, and the queer black hole we will talk about, but instead of that, I think those are we are going to talk about a week after. But today we will talk about the Auger sphere and the frame tracking. Those are very, very interesting things. This Penrose process and so on. So they're very interesting. This is the for the topic of next week. But what was it? I think So today we will talk about the Reissner-Nordstrom black holes. So those are Reissner-Nordstrom black hole we will talk about. Okay, so that's the recap of the previous lectures. Sorry about the delay of the. Sorry, my laptop has some problem. So thanks for this one. I think I can switch off and then use the blackboard to use it. Thank you very much. Okay, so fine. Let me. So recall that the y is equal to tortoise coordinate. So r star is equal to r plus rg ln r minus rg minus 1. So when you set the r is equal to r is equal to the rg, this becomes divergent, right? This quantity becomes divergent. So that if you just use this dr star from whatever r greater than rg to rg, then this becomes infinity actually. This becomes infinity. This becomes infinity. So therefore, it takes infinite. Infinite coordinate distance. So therefore, it goes to tortoise coordinate. R star is for tortoise coordinate. Okay. open for. So that's the yeah. My Chinese gets written also. I think do you need something in here?
Right, yeah. One.
Like this way?
Right.
Okay. Fine. Okay. So before going to the talk about the Reissner-Nordstrom today, let's a little bit talk about the Penrose diagram of the Minkowski space, because some part we haven't covered yet. Some part we haven't got. So the last time, if you start with the Minkowski metric, whatever, so Minkowski. And then, so when you introduce u is equal to tangent inverse t minus r, v is equal to tangent inverse t plus r, and then the region of u and v is less than pi over 2 minus pi over 2, and then it becomes conformal flat. So if you just do the metric ds tilde is equal to du dv and then minus 4 plus some factor omega uv d omega 2 this way, and then we introduce like this way. So this is pi over 2, and then here r is equal to constant, and t is constant become like this way, and so that's what we already learned. And we call it this one scribe plus and scribe minus, and I plus, I minus, I 0, like this way. Okay, so that's the thing, and then we can again introduce new coordinate. New coordinate is something like a t is equal to b plus u. In this case, here is a b direction. This one is u direction. Okay, u direction, and then chi is equal to b minus u. Okay, I think so. Here, u has to be greater than b. That's we need to introduce. Yeah, something like this. Okay, and you can introduce this new coordinate chi, so that the minus pi t plus chi is less than pi, and minus pi t minus chi and chi is greater than this. Okay, so if you use this relation, you can easily derive this. Okay. Then, if you write down the metric of this one, we can just write down that ds squared is equal to minus dt squared plus d pi squared plus sine squared chi d omega squared. So that's the metric, and this is called Einstein static inverse. Okay, and then actually So, how many of you learn about robots? I forgot the order. Friedman robots worker universe. How many of you learn about FRW universe? Can you raise your hand? It's okay. Okay, half of them. Half of them. Okay, then I think we should cover if you don't learn. So the so-called how to say FRW universe. So this is the how to say isotropic homogeneous universe. One can derive the solution. And then, I think if you don't know, I mean, it's fine. I mean, maybe I can talk about this one in future in this course. Okay. Let me write down first. This takes the following form. And Einstein didn't like the universe actually grow and so on. This dynamical. Einstein didn't like the notion of the so-called cosmological constant, and also the universe has its dynamical. So therefore, he first write down this A square. So A square T is equal to 1. Then it becomes the static Einstein. Anyway, he derived the universe to be, our universe become like this way. Capital T is of course time, and so on. But anyway, so then we can just write down. So this Einstein static universe can be written like this way. And then you can just draw the so you can draw. I don't know. I'm not good at the drawing of the figure. So you can embed this. How to say? I think most likely I will fail. So that's why I don't want to. So this region is embed. So this is the total cylinder is the Einstein static universe. But you can embed this Minkowski spacetime inside. So this is Minkowski. So the Penrose diagram Minkowski spacetime into the this Einstein static universe. That's you can embed by just since the coordinate is only like valid for this region, so you can just embed like this. So that's the This figure is written in some famous book by Hawking and Ellis. So anyway, you can there are lots of nice figures over there about Penrose diagram and so on. We will learn from now. And this is the one way to embed Penrose diagram to the Einstein static universe. Okay. That's what I wanted to mention. So, but I also wrote the Lindros space. I'm gonna skip Lindros space because this one needed some concept about so-called killing horizon as I show in the figures in the slide, and so I will skip this one. By the way, so you guys just learned the GR from Cosimo. I don't know. Some of students are here from Huda undergrad. How many of you took the Cosmos lecture? Okay. How about Eden's lecture? Eden's GR. Fine, Eden. Nobody. Okay. Okay. Fine. So or you guys just do not want to raise your hand. So in Schwarzschild, if you want to talk about Schwarzschild geometry, I can talk about a bit more, to be honest. For instance, does anybody study this one, gravitational redshift? Have anybody learned this one? Yeah. So please raise your hand once if you learn this one. Okay. Okay. About half. How about let's see. How about deflection of light? So this one is something like there's a star here, and if you just omit the whatever electromagnetic wave, the frequency here at the R is equal to whatever solar mass is different from the R's, the frequency at the receiver at the, on the R. So there is a redshift. That is called the gravitational redshift. I mean that you can easily derive from Schwarzschild metric. How about diffraction of light? Does anybody learn diffraction of light? Oh, only few. Okay. What?
Can't derive it.
What? So if you have a star and if you omit the some whatever particle or light, it becomes diffraction of light is something like it's just because of they obey anyway. So they obey the geodesic, but the angle will change. So this angle theta, and then there is some how to say the shortest radius like delta. There is some correlation between delta theta is equal to some function of delta and the mass and so on. Have you ever learned? Please raise your hand if you learn it. Okay, again, similar amount. Should I cover it? I don't know. I should cover it. How about how about the opposite? Even I cannot pronounce it precession. Or Mercury. Or Mercury. Have you ever learned this one? This one. I think in Chinese, I think this then Yidong.
Mercury precision, right?
Huh?
Mercury precision.
Yeah. Mercury, like if there's a star and there is something rotating like this way, there's gradually just shifted like this way, like this way. Have you ever learned this one? Oh, okay. Half of them are learning. Okay. I don't know. Those are we can learn by using Schwarzschild metric. I'm moving on to today. I'm going to talk about Reissner-Schneider, but if you guys want, I can recap this one. This one. I'm not sure if I should do that. I don't know. But you guys just do not learn Freeman, Robertson, Walker so much. Things like not that is equal to it should be equal to h inverse. That's what it should equal. Okay. Again, f should be h equal to f. Okay. That's what we get. Like in Schwarzschild case. And then also we can just consider the equation motion. Bianchi identity. No, equation motion. of the f mu for f mu, then del mu f mu 0, and this one can be written as follows. I mean, just instead of the ordinary derivative, you need to replace by covariant derivative. So therefore, you need to take into account the Christopher sample. Okay, then f is equal to partial r fr0 plus 2 over r fr0, and this is equal to since we already knew that if fr0 is non-trivial, right? So from here, f mu nu you only have electric field. F mu nu is something like a 0, E1, E2, E3. There is no magnetic field because I mean with this assumption. Okay, that's why I call it electrostatic. Okay? That depends on R, like this way, and minus E1, minus E2, minus E3. And the rest is 0. So therefore, this is a non-trivial part of the equation. Okay, and then this is given by f of c and phi double prime. Phi prime equal to 0. Okay, so we need to solve this equation. So that's easy to solve. And since we assume spherical symmetric, so it's easy to solve this equation by setting f. So phi prime is equal to q to the r squared. Okay. So this is electron. So electromagnetic electric field. Sorry, it's better not to memorize this one so far. Electric field. And plug down into here and solve the third equation. It's very simple. So far it's very simple. What we have been doing is very simple. Okay. And substitute this one into the third equation. Okay, f is equal to h, and phi prime is equal to q over r squared into number 3. Okay, number 3, and then this equation becomes something like this way. Then f is indeed equal to r f prime is equal to 1 minus alpha q squared r squared. So that's the what we obtain from number 3. Okay, just need to solve this ordinary differential equation, and then it's easy to find a solution, which is something like which is very easy to see that the Rg is equal to R, and then alpha G squared. And then again, when q equal to 0, we need a Schwarzschild solution, black hole. So therefore, Rg is equal to 2m divided by c squared, 2mg divided by c squared. So those are the nowadays called Reissner-Nordstrom. Nordstrom, Reissner-Nordstrom solution, but this one is also considered by a while. In addition to Reissner-Nordstrom and while, and also I didn't know. I don't know what's this. I don't know. And my laptop is broken, so unfortunately. There are not only Reissner and Nordstrom consider this case. There are 2 other guys also made a conclusion. This is the Reissner 1916 and then computation. And Wilde in 1917, and Nordstrom 1918, and then in 1921. So that the it's I am published date published year, but these are the people who contribute this solution. Okay. Fine. So the difference is clearly this guy. Okay. So therefore, difference from Schwarzschild is this one over R square term. That makes the structure much more interesting. So the metric is become really like this way. -1 minus now set. Okay, so as I mentioned, so I don't like G and C. So from now on, I just set like this way. If you want me to talk this whatever gravitational redshift and so on, maybe I may have to restore this one. But anyway, so for time being, let's set this one. Okay, and then so the metric becomes like this way. Fine. So that's what's the metric is about. And here we can just write down like this way, minus R plus. So it becomes quadratic equation. There is some f equal to 0 will give you the two solutions. And then R plus minus will be given by as follows. R plus minus, this is equal to n squared plus minus square root n squared minus 4 q squared. That's what's really happening. Fine, so that's the case. So capital Q is indeed capital Q squared is equal to alpha times Q squared. So this is the alpha is some unimportant normalization, which I already erased. Seems like which I already erased. So I just rescale the electric charges. The capital Q is electric charge. Okay, as you can easily see. Fine. So therefore, since it becomes quadratic equation, so you have two roots. Okay, which given by m squared is equal to. So then the important thing is the how does this part behave? Fine. So if the m is less than q or whatever, so q can be positive or negative, so that I just take absolute value. If this is the case, this part become negative square root is imaginary. So there's no imaginary, no real solution to the FR is equal to 0. FR is of course this guy. FR is this guy. So this is analogous to the m equal to less than m is negative for Schwarzschild. Okay, I don't like to write the Schwarzschild black hole. So this is analogous. Okay. So therefore, the dimension, I think last time I talked about the cosmic censorship conjecture. This is 1969 by Penrose. Prohibits the next singularity. Okay. So here again, if you compute the curvature of mu nu rho sigma, or mu nu rho sigma is become the. Did I compute this one? Unfortunately, I don't compute this one. Anyway, so one of our is some power, positive power of this one. So therefore, true singularity locates the r equal to 0. But so this f equal to 0 becomes some kind of like again event horizon. But here, once you have the if the electric charge is greater than the mass, then there's no event horizon. So which means that the next singularity. Okay. So therefore cosmic censorship. So this is not real. Not the real solution. But I have to mention that the Reissner. Okay, sorry. Before going that, I have to mention that. I have to mention one thing. Reissner-Nordstrom black hole. It's believed not to exist. What are the reasons? Why the Reissner-Nordstrom? It is believed that the Reissner-Nordstrom black hole is.
You mean in nature?
In nature.
Well, because you don't have charged like very bodies with a high electrical charge in nature.
Yeah. So star prefer to be the energetically okay. The stable object. If it is the charge is neutral, there's how to say. Life is much more stable. But if you have a charge, you have to attract many things. Okay. And so that you just attract lots of the opposite charges. It's like anyway, Mani or Schreiber. Anyway, so if you're have charges, you have to attract the opposite charges to become neutral. Okay, so that it is believed Reissner-Nordstrom solution black hole does not exist in the nature, but theoretically even this is not real solution because of the negative singularity. Okay. So therefore this part is not. And also one thing one can do that some interesting estimate. Okay. So electron in this unit, G equal to 1, C equal to 1. Electron mass of electron is much less than QE actually QE. Okay. In this case, so we can ask a question that can electron become black hole? Because of course, due to cosmic censorship, we can exclude this possibility, but we can just make some rough estimate. So what are the Compton lengths? Compton length of the electron, which is just h bar over MEC, and this is roughly speaking 2.4 cross 10 to the minus 12. So this is the Compton length. On the other hand, the Schwarzschild radius. So 2mg over, unfortunately, I already restored G and C. And this is roughly 1.4 cross 10 to the minus 15, 8 meter. So the order is totally different. Okay? Order is totally different. So if, using electron, you cannot, probe the scale of Schwarzschild of the electron. So it's impossible to understand the black hole nature of the electron. That's first thing we can mention. And also we can compare the Planck length, which is the square root of the square root hc over g. Sorry, it's opposite. G over CQ, and that is 1.6 cross 10 to the minus 35 meter. Okay. So therefore, Planck length is much larger than the Schwarzschild radius of the electron. Okay. So therefore, if you want to if there's a way to compress electron to the level of the Schwarzschild, but even you have to go through the Planck length, which means that around this scale, the quantum gravity is most important. It becomes quantum gravity is in this case quantum gravity is important. So therefore, classical GR will break down. So therefore, there is no way to predict the black hole nature of the electron. So that's one thing. Another. So therefore, anyway, there is no way to prove gravitational nature of the electron if you compare with this scale. Okay, so then let's move on to the more realistic case. Even though it's not it doesn't exist nature, it's like this way. Strictly mass is strictly greater than the charges. So in this case, the R plus is outer, R plus R minus is called the outer event horizon, and inner event horizon. So that's for outer and inner horizon because they are real number, and of course as you can easily see, R plus is greater than R minus, and of course they are all real. They are all real solutions. Okay, so like this. Fine. So let's take a look at the causal structure. Before erasing this one, so as you can easily see, fine. So I call it this part. Is A, and this part is equal to B. And let's do the naive analysis. So R is greater than R plus, A is negative, and B is positive. Do you agree with that? Because R is greater than both are positive, but they have a negative sign here. So A is negative, right? And B is positive. So this means that the T coordinate, this means that the T is time coordinate, time coordinate, and R is the space coordinate. On the other hand, R is R plus, R minus. A become positive and B become negative. Do you agree with that? Is it okay? So this means that the time coordinate it becomes space coordinate, and R is the time coordinate. Okay. How about this one? So the N again become negative and B become positive. Okay. So therefore T is the time coordinate and then R is space coordinate. So those are the structure we encounter. We encounter. So as you can easily see from here, you can just see that the structure is a bit more complicated than the Schwarzschild.
R minus and R minus.
Oh yeah. Thank you so much. Okay, you're right. Okay. can erase this part. I hope I. Okay, let's keep for time being. And again, we introduce called tortoise coordinate and so on, and then analyze the causal structure of the space-time. That's exactly what we have done in Schwarzschild. So again, tortoise. Okay, wait. Tortoise coordinate is the in fact the R star is in fact equal to dr divided by this 2m over r plus q square over r square. Okay, which is the okay. And then just do the integration. You just do the integration. dr square is equal to this one. Then you will get r star is equal to r plus 1/2 kappa plus log natural log r over r plus minus 1 and plus 1/2 kappa minus natural log r minus over r minus divided by 1. And then kappa plus minus is equal to r plus minus minus r minus plus divided by 2r squared plus 1. Okay, so that's the tortoise coordinate and the right down the metric. That's we already did many times. No, not many times. One time in a short shot, and then we are going to do many times for this exercise. And even your homework, you have to do that. And then, as we did in the B and the U, is the new coordinate t plus r squared and t minus r squared. This is new coordinate. Okay, so B equal to constant, U equal to constant become null. Okay, so no geodesic. That's how we choose this tortoise coordinate. No coordinate, radial no coordinate U and V, and then the same exercise U plus minus. We just introduce e to the minus kappa plus minus U and V plus minus. This is the difference from Schwarzschild. We have only capital U and capital V, one kind. Here you have a two kind, depends on sign and plus minus. Okay. Fine. Fortunately, yeah. So like this way. Okay. Then the metric. The first, let's use U plus and the V plus instead of T and R or T and R. Then the metric becomes like this way. So I don't care about the compound factor. Some complicated compound factor, omega R, du plus and dv plus plus r square d omega 2 square. Okay. So that's the. So this is some complicated. So it's in write down the lecture notes with a compound factor which only depends on r. Depends on r coordinate. And then important thing is this is the smooth at or smooth non-singular. I think non-singular is better. Non-singular at r is equal to r plus in this case. Okay. So therefore, we can just avoid this coordinate singularity in the metric if you introduce r star. Okay. R star. Fine. So you understand why the B and U are the new coordinate? Do you understand this one? Why T plus R star, T minus R star the new coordinate? Do you understand that? How do you derive this one?
Yeah, because if U and V is equal to constant, it is a light ray.
Yeah, it's right late. So if you use this metric, dt light ray, we can obey this equation is equal to 1 over this one. This equation, okay? So this equation, with the r squared, yeah, r squared. So it obey this equation. If you forget about the spherical part, there's two sphere part. So therefore, this r star. So this is what the Finkelstein did, okay? So the Finkelstein did this one is as first around 90, around 60, 50 something. It took like many years to human being to realize to introduce this coordinate. So yeah. Anyway, so we often miss this kind of like a simple step. It often happens for history of human being or science of human being, to make a simple step. It takes many times, many years. That's unfortunately the case. And then if you write down this B plus and the B minus U minus like this way, then B plus U plus, so B plus is some function R. So this is the some e to k plus R. Anyway, you have to write down R plus and R plus, R minus, and some power. Kappa plus kappa inverse. So therefore, so once this fits R, U plus times B plus become constant. So therefore, R is equal to constant is become like this hyperbola again. This is the R is equal to, maybe it's better to use the yellow line. Maybe. So this is the like this way. My drawing, sorry. So these are R is equal to constant line. Fine. And then you can easily see what happened. R star is equal to R plus. Okay, R plus. Once you plug this one into here, okay, so this becomes 0, right? So therefore, this quantity becomes minus infinity. Okay, and plug down into here, you get the B equal to 0. Okay, so therefore B plus is equal to this corresponding to R plus is equal to 0. R is equal to R plus. Okay, R equal to R plus. B plus is, do you okay? Are you okay? So if you plug R is equal to R plus, this guy is divergent. Okay, minus infinity. Plug that into here. You get fine. You have to be careful. This here K plus is, so we pick K plus. And K plus is a positive quantity. Okay, so this is also important. Okay, so that's also important. But as you know, so if you use this U and V, capital U and capital V coordinate, I don't like it. Anyway, so capital U, my capital U is something like this way, capital U, and then you can just step inside horizon, outer horizon. So this is the outer horizon, and then R plus, so they become like so this is R constant, but now since R is less than R plus, this become negative, okay? This quantity become negative, okay? And negative times negative is positive, so therefore in this direction, okay? So previously R is greater than R plus, so here is the constant and R plus, greater than R plus. So this quantity become negative, because there's a minus sign, this is positive and positive, okay? So therefore, but now it becomes space. So here the R is constant is the like a time lag. So which means that the R is a space like coordinate. But now here R is constant become like a how to say space like. So therefore the R is become time like coordinate. Okay, do you understand what I mean? So R is here is space coordinate, but here R is the time coordinate. Okay. Fine. Any question at this moment? And then eventually we will hit. R is equal to R minus. Okay. But in this case, we need to use new coordinate. U plus. That's why we introduce U minus. Okay, so now, we will use the U minus and the B minus coordinate. Okay, U minus and B minus coordinate. What's the merit of this one? So now, so we want to prove. So here, B plus is equal to 0. Sorry, no, B plus equal to 0. Did I make a mistake? Seems like I made a mistake. Sorry. R star. Did I make a mistake? This is U plus and the B minus, B plus. Which one is better? Because as I mentioned, if I put this one, R equal to R plus, this equal minus infinity, right? And then here minus infinity plug into here. This also U plus is also equal to 0. Which one goes to 0 and which one goes to constant? Am I doing some stupid mistake? Wait a second. Which one is the R equal to the? Which one becomes 0? Both become 0.
U plus.
U plus becomes 0.
Because B is minus infinity, right?
B is minus infinity.
So it should be B plus. If it is plus, then it is minus.
Then this becomes 0, right? No?
Yeah.
This becomes 0, right? How about here? R star is minus and plus infinity, but here minus k plus u. So this also look like a 0. Am I missing something? Okay. Let's postpone this and move on. Here you have a B minus and then U minus, like like this way. And then the metric is again become, if you use this metric, minus omega tilde r du minus dv minus plus r squared d omega squared. So this is again, metric is very simple. And then non-singular at even r is equal to r minus. R equal to r minus. So what if? Okay, so now we need to pick. Yeah, so our kappa minus is clearly negative. Clearly negative. Okay. Kappa minus is negative. But if you put r minus into here, it becomes a negative infinity, and this is also negative quantity. This is plus infinity, and plug that into here. The kappa minus is negative and minus. Okay, so this becomes infinity. Okay, so this is okay. So b equal to 0 is now the horizon in that case. Looks to me that's the case. Sorry, I think which one is correct? The opposite? Is it the opposite? Sorry, I got confused.
What about the second term of r star? If r equals to r minus.
This term?
Yeah. R minus is negative.
R minus is positive.
Yeah, r minus is positive. The argument of logarithm is
Negative.
negative.
Yeah,
Is it-
that's true.
is it possible?
That's a good point.
But it only appears in the exponent, so we can treat it as some kind of minus sign. So
That's a good point. So if you plug that one into here, what's going to happen? That's true. That's true. You're right. You made a good point. So it's only appear exponent. That's true. So that, I mean, for instance, if you put the k, or for instance k minus, kappa minus, and plug that into here, you get the 2 kappa plus and ln r over r plus 1, and this is equal to r plus minus 1, and then kappa 1 inverse 2 kappa plus. So it's no problem. So this one will give you factor, and you need to take into account this sign actually. You're absolutely correct. That's why I think yeah, that's fine. Okay, I don't know which one becomes the 0, to be honest, at the horizon. R equal to 0. Okay, R equal to R minus 1. I don't know which one. It looks to me B minus becomes 0. Because the R plus, R minus, right? This becomes minus infinity, and this is minus sign. So therefore plus infinity. But here you have a negative sign. So therefore this becomes the 0, looks to me.
but it's the same thing for u. Like
Same thing for you, right?
both u and v vanish simultaneously.
Looks to me that's the case. That's why I got confused.
So we do not have a coordinate to cover all space-time.
You're right. Sorry about it. So the same as Schwarzschild. Schwarzschild also the same. Both are the horizon. Sorry. Sorry about it. Both this line, both lines the same. is equal to r minus. Sorry, thank you very much for the help. Both are horizon. This is both are the horizon, and this both are in the horizon. Okay, you're right. Thank you very much. Both are the horizon, in the horizon. Thank you very much. And then what we need to do is the u minus b minus is equal to minus to d to kappa minus r. Sorry, r minus. So therefore, in my convention, this is b, and this is u. Sorry. Sorry. Minus r and r minus, and then times r plus minus r plus kappa plus. Fine. So this is the what we have. And if you look plug in r equal to 0, this becomes a negative quantity. So therefore r equal to 0 will show up like this way. And then this is r equal to 0. Like this. That's what I want. Okay. So far, let's write down a Penrose diagram by using this one. You're right. That's why I got confused. So you start with the scribe plus, scribe minus. I think I need a bit below actually. I need a bit more space. Scribe plus, scribe minus. And you encountered the horizon like this way. So this is r is equal to r plus, and r is equal to r plus. So this is a u is constant, and b is constant. Okay? So therefore, you can extend the space time to the past and so on. And now, after that, you encounter. So here you just start with the r. So you just go to r goes to infinity. R goes to infinity is the space infinity, and just enter the horizon by that common right cone, and then you enter. So here around here you have r is equal to r plus. Okay. So now I call it space region 1. And the space region 2, and the space region 2 should be here. Okay, and now r is the kind of like a time coordinate, and here the time coordinate r is the space-like coordinate. So therefore, it's region 1 and region 2. And depending on which region you go, so last time, how did I call the region? Yeah. So I called this one, I don't know, it depends on how you call it. Maybe I can call this one 3 and 4 as before. Okay, you're right. So this is like almost like a short shell. Like a very look like, but there's enough horizon, and you can extend this one. So I call it, I don't know how to call it. 1 prime, 3 prime, and 4 prime or something like that. So then you can extend this one to the furthermore. It's not like this one. 1 prime, and then 3 prime, and 4 prime. Okay, like this. Is it okay? Is it okay? And now r equal to 0 is really singularity. So r equal to 0 is singularity. Okay, so therefore here we encounter some singularity. So this is r equal to 0. So that's how the space Penrose diagram looks like. Okay. Is it okay? So you start with R is equal to infinity and the falling light cone, and then you first encounter hits the event outer event horizon. But further you can just move on, and then encounter this is R equal to inner horizon, inner event horizon, and then we can just still move on. Since the causal structure here R is infinite, the time-like, so therefore light cone become like this. So and then you can extend, in fact. So you can extend this one conformal diagram like this way. I know, and then. Roughly speaking, it become like, hopefully it's visible from the back, and then you can extend the space structures like this way. Sorry, my drawing is horrible now because I cannot, even with my height, I cannot reach already. So just do some cheating, and then yeah, become like this way. Like this way. So you just go like that. You can extend the space-time to the infinite long into the future, infinite future, and also. Here we can extend the past like this way. So these are the Penrose-Cotta diagram of the eternal Reissner-Nordstrom spacetime. Okay, let's take a break. If you have a question, tell me. Yeah, thanks your computer. It was very helpful.
Let's assume the Reissner-Nordstrom black hole exists.
It doesn't exist.
Now let's
in nature.
assume.
Huh?
Let's assume it's
Okay.
exists. So where all the charges will be collected? In the singularity or where?
In here, singularity.
In the singularity, yeah? All charges will be collected like mass of the black hole is in singularity.
Yeah.
Right? The charge will be
Yeah,
collected.
yeah.
So in that case, if there is a charged particle outside the event horizon,
Okay.
it will not be affected, influenced by Coulomb force, right? Because charges in singularity inside the black hole, it cannot affect the charged particle outside the black hole.
No, it can affect.
How? Because the causality, any kind of effect cannot escape the event horizon.
Because the space-time knows the charge.
Yeah, it is. Yeah, it affects as a gravitational force, not Coulomb force. It affects as a gravitational force, right? I mean, it affects the same for positive and negative charges also.
No, because I mean, space-time has F mu, right? The T mu is not zero. Space-time T mu is not zero.
Yes, you are saying that all charges will be collected in the singularity, in one point.
But space-time has a non-zero T mu.
What do you mean?
Electric field is everywhere.
This is my question. How it can be happen if it is in the singularity? How can electric field everywhere? How it's possible? There's no way that electromagnetic electromagnetic lines can escape the event horizon, right? If the charge inside the black hole, there is no way that the lines can escape the black hole or the event horizon.
But that's the nature of eternal Reissner-Nordstrom spacetime. I mean, we need to assume that the electromagnetic field is everywhere.
Then we have to check the definition of event horizon.
Why not? Because we have the white hole here, so you can just have the electromagnetic field that can emit here. Right?
Then we have to go down to here.
So if you are here, if you are staying here, so the electromagnetic can emit from past the white hole.
White holes do not exist.
That's why that's the nature of eternal space-time.
Well, let's assume like this. This is singularity. This is in the horizon.
Okay.
This is outer horizon. So all charges will be collected there. So the electromagnetic fields cannot escape if it is a simple charge, let's say it's a positive charge, then electric field line like this, right?
But that's not how you think about it. That's not how you think about GR.
Yes, so it cannot escape.
That's not how you think about the GR.
How do you see?
But quasar structure, if you look at quasar structure, you can easily see that the light can move from here to here. So it's a nature of eternal Reissner-Nordstrom.
Can you explain this in this figure?
No, so this is not right way to think. That's not right way to think. It's already, if you have singularity, the electromagnetic field are everywhere. Already everywhere. Already everywhere.
Okay.
That's how we solve the Einstein equation. So T mu is non-zero for everywhere. That's the nature of a Reissner. So that's not right way to think about it.
Okay, then the question I can ask in the next lecture after understanding this figure first. And the next question is, let's assume this is the singularity, and this is a inner horizon, this is the outer horizon. And here, T is time, right? Air is space. And light cone will be like this.
Yeah.
Right? In here, T is radical coordinate T. So it will be something like this.
Yeah.
In here, it's again time, T is time coordinate. It again will be like this, right?
Yes.
So unlike the Schwarzschild black hole case, it's not destined to collide with singularity.
No.
It's not destined.
No.
So the particles can be collected in this region also.
Yes.
Right?
No. Yeah. It's like this. The quasar structure, you can just move on to without hitting here. So you can easily see from the quasar structure from one side. It's a light cone is always like this here. So therefore, you can always move to here and here and here and here and so on. Infinite way. So that's the nature of eternal Reissner.
Yeah, so they can also go there.
Yeah.
Maybe the charge will be collected here in this region. So it's not right. It will be
Everywhere.
It is in singularity or it's here?
No. The electrostatic field is everywhere.
No, charge. Part charge, part proton enters the even horizon. It's electron enters the even horizon. Where they will stay? They will stay there or there?
Space time.
Of course, Mr. But in which part of space time?
Everywhere. So there's an electric like a charge. That's not right way to think.
No, I'm not talking about the electric field.
Okay.
I'm talking about the charge, particle.
Charge only knows about the space-time. Metric knows about charge. It's not the object.
Let's say particle, electron enters.
No, there's no particle.
Let's say electron.
No, there's no electron or particle. So it's just charges are only encoded in the space-time metric. That's the only information. So it's not right way to think the charge is contained in the singularity. It's not right way to think. Charge and mass information only contain the metric.
Yes, I understand. Let's see one scenario. Electron is coming from infinity. So where it will go? It stays there or it goes to there?
Depending on the yeah. Huh?
So angular velocity determines it can stay there, it can go there, right?
Depends on
So not necessarily that all charges should be collected in the all particles. All collected needs to be collected there. Can be collected there. If particles can be there, then charges also can be there.
I mean, if you look at the from outside, or if you look at the people from outside, the net charge is less. What's your question? I don't understand. If you put some electron into here, and if you stay outside the observer, net charge from outside is increase or decrease depending on the sign of the electron. Depends on sign of the charge. Electron charge. Depends. Increase or decrease. Net charges from outside observer. That's the only thing. It's not right way to think the charge is stored in singularity and so on. That's not right way to think.
So you cannot think it's charge stored.
No.
So how would you answer the question where will charge will be stored?
That's not right question to ask.
You cannot ask.
You cannot ask this question. The space-time knows about the charge. Because electric field, electrostatic field knows about charges, but it's not right way to ask the question where is the store? Where is the store?
But if I ask a question where all mass will be stored, you will obviously say that it will be stored in the.
That's not right way to think.
For example, what about the Schwarzschild?
Schwarzschild cases, that's not right way to think. It's only know about space-time metric knows about the mass. Let me get something.
I don't know.
Yeah, I'm a PhD student. Yeah, yeah, no, I am taking this course. I'm taking this course. Yes.
You can take the course and go to university.
Yes, any course. And I have to take some course from either physics department or some other department as an interdisciplinary. So I've decided why not this one. I've heard good things about Satoshi. I've heard good things about Satoshi, so I decided to.
You can keep this course.
No, I've never finished. I've heard good things about you. So, about you.
Can I
I'm from Russia, so I'm on the graduate school. the Russians. I'm not sure the name. You're a student of physics. Oh, interesting.
Okay, so let's get started.
So is it recording? Okay.
So okay, so as you where did I put my lecture note? So as you draw here, so starting from here, if you use the rocket, like a very, very nice rocket, or like a SF and so on, SF, start from here, one can just always light points or like this, so you can always move to the another universe and so on. So without hitting R equal to 0 in the case of eternal Reissner-Nordstrom, okay? Eternal Reissner-Nordstrom case. So that's the difference between the Schwarzschild and Reissner-Nordstrom. You can just extend to like a infinite many times of this pattern of the space-time structure.
So the other can exist oscillation at R minus.
R minus. So this is the R is equal to R minus, R equal to R minus, and the R equal to R plus, and so on. R equal to R plus.
Seems like oscillation.
Huh?
Seems like oscillation between.
Yeah, so the R coordinate will change. Yes. So it's a very, very, very mysterious thing. But as we already showed in the black hole, so Schwarzschild black hole, so the cosmic Penrose diagram become like this way. Penrose diagram become like this way. So this is eternal. But in reality, what's going to happen is as follows. In reality, what's going to happen is something like this one. So this is R is equal to R 2M I0 like this. So in reality, what's going to happen like this way? So the star is the this yellow part is the whatever the position of some matter, okay, and eventually after the whatever. The star run out of energy of to support the gravitational collapse, and then you hit the singularity like this way. And then this line is R equal to 2M curve, and this is the so therefore I call it the 1 and 2, and then 3 and 4. In reality, we cannot see 3 and 4. We have only 1 and then 2 here. 2 here. Yeah. We can do the same thing for the Reissner spacetime. Reissner spacetime. In reality, or of course, the Reissner-Nordstrom it is believed that isn't a Reissner black hole, but if there is, the what's going the scenario is as follows. Start with again. past infinity I minus, and this past spatial infinity, and then there is something in the middle, the center of the star, and then something strange will happen. So I 0. So around here it's very similar to Schwarzschild, but now we have the, so this is R is equal to R plus and R is equal to R minus. Sorry, you have to roll it anyway. So like this one. So there is a singularity, and then it's hard to draw like this way. And you repeat. Like this. Actually, the style of corruption does not halt into the singularity. So here you can easily see that the matter inside a star is the actually it hits to the singularity. But in Reissner-Nordstrom case, we never encounter that the matter hits into the singularity. It's because the electron, so this matter has the electric charges. So therefore, electrostatic repulsion halts the gravitational collapsion at some point. As we know, the electron, so we make an estimate, right? So compare Compton length, Schwarzschild, and also the Planck scale and so on. Okay, we cannot anyway squeeze electron into the Planck scale, and also let alone its Schwarzschild radius, because Compton length is way larger than those scales. So therefore, if you just try to in reality, if there's a matter with charges and go to the gravitational collapsion, electrostatic repulsion will halt or stop the gravitational collapsion, and then eventually just bounce it back, and then just go bounce and then collapse and bounce and so on. Eternally. So that's the space-time structure. So we can just make rough estimate for what's going to happen in this kind of like a surface of a star. Surface of star. So surface of a star is kind of we can consider as pressure is equal to 0. Pressure equal to 0. So you can consider some kind of free fall of charged object. Of course, the particle on the surface of star should have a charges, okay? But it's pressure equal to 0, so that's a free fall. However, it's not a geodesic. It's not geodesic. Why?
It's under the effect of electrical repulsion.
Good point. So now, because the particle on the surface also should have electric charges. So therefore, there must be some electric interaction between inner matter and then the particle itself. So therefore, we have to solve the Lagrangian, which is as follows. It depends. I mean, Lagrangian is something Z alpha beta. Then in my lecture notes, like this one, alpha x dot beta plus q times a alpha x dot alpha. We have to solve this equation in the Lagrangian and solve this Euler-Lagrange equation. Okay. G alpha beta is the Reissner-Nordstrom the metric here, and then we need to solve the if you have only this one, you just Euler-Lagrange equation is just geodesic. Okay. However, here you have electric interaction, so I have to solve this equation. And what's going to happen? Let's do that. Okay. So again, we have something like a zero is equal to, I forgot, q to the over r. So that's what we have. And then if you just write down this Lagrangian, we can just write down 1/2 delta t dot square plus delta inverse r dot square plus r square theta dot square, and then minus r square sine square theta phi dot square, like this way. Plus q capital Q divided by r over t dot. Here dot x dot means it's just a derivative with respect to proper time. Per time. So that's the equation, and delta is this f. I think I should use f actually. Sorry, instead of delta, I should use f. F of r. F of r. F of r. Where f of r is 1 minus 2f over r minus the, what was that? Q square over r square, depending on like this way. So that's like this. So also, and then we have to solve the equation of motion. Equation of motion, and then so let's solve the equation of motion. So the Euler Lagrange equation it becomes like this way: L alpha and del L x alpha equal to 0. So now there's we can just consider, like for instance, t derivative. T derivative is something like this one, dl del t dot bar d tau, and then there's no t dependence here. So as you can see, there is no t dependence here. So this, if you replace x alpha by t, second term does not contribute. Okay? Does not contribute. And then this is equal to del. So d tau f of t f of r t dot and then plus q r, like this one, is equal to 0. Okay, is it okay? So you just take the t dot. If you look at t dot part, this is the t dot part, and then what else? T dot part is here.
Not 0, but dl over dxl.
This one?
Yeah.
This one is 0, because there is no t dependence here.
Right.
Yeah. So therefore, this inside is constant. So this is constant. I call it this epsilon. So I call it this is epsilon, and also this is phi dot of d tau. And again, there is no phi dependence in here. Phi dependence in here, and this is equal to. So the second term does not contribute. D tau, and then what was that? So the equation become r square y dot, and this is equal to 0. Okay. So phi dot only appear here. Okay. Phi dot only appear here, and then somehow I put the theta equal to 0 somehow. Okay. Actually, this is in fact r square sine square equal to 0. Okay. But now, so we only consider the particle on the surface of the star. Okay. So therefore, so we don't assume any angular momentum. Okay. So therefore, so this term is actually dl. You can easily see this is the angular momentum of the particle. So you can usually set this one is equal to some angular momentum L constant, which is constant, but we can assume this one is 0 for in our consideration. Okay. And epsilon can be considered some energy of the particle on the surface, okay? Because it's just t dot derivative. Okay. Any question at this moment? And then we can just solve this equation. It's very straightforward to solve this equation. Okay. So in the so metric become like a d tau square is equal to f of r dt square minus f of r inverse d r square. Okay, so that's the case. And take the derivative with respect to the tau square. What you get is as follows. So 1 is equal to f of r and dt d tau square minus f of r inverse dr d tau and square. Okay. And I call it this is equal to t dot. So this is t dot and this is r dot, t dot square and r dot square. R dot square. And then we just need to use this fact. In fact, t dot is equal to what was that? F times fr times t dot is equal to epsilon minus q capital Q over r. Okay, so that's the from here, and plug that one into over there. And then what you get is the I hope I'm not doing something wrong. Let's see. R dot square is equal to f of r square t dot minus f of r. Okay, I hope I'm doing correct. I think I'm doing correct, right? And the t dot is like f of r t dot square. Yeah, square. Sorry, square. And f r square t dot square, we have this one. You can plug that into here. Why the sign is not correct in my lecture note? Somehow sign is not correct. It's okay. Sorry. So this is equal to epsilon minus q capital Q over r square minus f of r. Okay, f of r. Okay, and then we just write down this one is equal to epsilon square minus epsilon q r and plus q r square. R square, and f is something 1 minus 2m over r minus what was that? Q square over r square, and most likely plus sign here. Is it okay? Do you agree with my computation? Yeah, seems like okay. And then I call it this one, everything here is equal to, so everything here.
It should be a 2.
Thank you so much. This is 2. You're right. And this is equal to minus B effective of the R. Okay. So this is kind of like kinetic energy for the particle on the surface, and V of effective R can be understood effective potential. And if you draw this effective potential, it's roughly like this: 2 minus. I'm really bad at calculation, so correct me if I make a mistake. 1 minus 2. Oops. I don't think I can do the computation. 2m over r. Okay, minus 2m plus 2 epsilon q. Okay, and then minus sign, and then 1 over r, and plus.
No, 2m should be with a plus sign. It's minus minus.
Here plus sign?
Oh, V effective is negative minus. Okay, sorry.
Is it okay? Is it okay? So far it's okay. And the QQ, QR square, this should be negative, and then Q square over R square. So this is a V effective. Okay. And the Q, small q are the charge of particle on the surface, and the capital Q is also the charge of the inside a star. So this should be the same sign. Okay. Okay, fine. And then R is equal to about M. R is equal to about M, and so on. And if you write down this one somehow, so that is actually, this is the derivation of the, actually, if you look at the Townsend lecture note, this actually is the exercise. I did this, his exercise, and then it become like this way, like this way. And there is some R and B effective. There is some repulsion because of this 1 over R square, 1 over R square, and then become like this one. So there is something, space. This is R is equal roughly R minus. So therefore, if you just move R is less than R equal to R minus, R equal to R less than R equal to R minus, there is some electric repulsion because of this B effective potential, and bounce it back. And bounce it. So I mean, you can just bounce it back like this way, or maybe I don't. It depends. So like this way, you just bounce it back and forth like this way, and then you become like this. You become like this. Okay, so that's how the surface of the Reissner-Nordstrom in the, if there exists reality, become like this way. Again, so any particle, any observer in the causal spacetime, what is that? So from the past infinity spacetime, you can just always go to the escape from the singularity. Because causal spacetime, you don't need to hit, no need to necessarily hit the R equal to Z. That is genuine singularity. In the case of Reissner-Nordstrom. So that's the difference between the Schwarzschild and the Reissner-Nordstrom. Any question at this moment? So if not, I will move on to some other particular cases called extreme. M is equal to capital Q. So then, in this case, the metric become like this way. square is equal to minus 1 minus m over r square dt square plus 1 minus m over r minus 2 r square plus r square d omega 2 square.
I'm sorry, I have a question about
Yes,
this.
yes.
So can the coefficient before the 1 over r be negative? That would mean there all the particles like scatter to infinity or something. Because
If this is the negative,
yeah, then there would be no well.
yeah, no, wow.
And-
So,
and
yeah,
every-
I think so.
every particle would
I think so.
fly out.
I think so, but that doesn't happen if you correctly evaluate this one. I think sorry, m is less than q. No, m is greater than q, right?
Yeah.
That's the assumption. And epsilon and q is very small if you assume this one, and then this is positive, and so on. I think if you do the correct estimate, I think it will become like this. Yes.
And charges are dimensionless here.
Charges are, let's see. I don't think so, because I mean, so in the metric m and r, right?
Yeah, because then the dimensions don't match. You have q squared over r squared, and then you have q, and all of it squared. Is small q dimensionless?
I think so. I think so.
So it's like a fraction of.
Yeah. I think so, because I mean, so Lagrangian is what g alpha beta dx dot, sorry, x dot and x dot and 1/2 plus q mu d x dot mu, and then
Yes, if we're counting dimensions, there should be a mass somewhere.
what's happening? So this is clearly dimensionless, right? It's a dimensionless, right? Dx over d tau is dimensionless, right? This is dimensionless. This should be dimensionless, which means mu is the mass, q is the has a mass. What's going on here?
I think like the mass is missing because the mass should usually be in front of the first, and then and here we kind of normalize, divide by the mass, right? Maybe it's q over m.
Maybe q over m, maybe something like that. Yeah, I think so. Q over m. You're right. You're right.
Then the final formula would somehow change.
Something like this one. Yeah, you're right. You're right. Thank you very much. You're right. You're right.
Okay.
Thank you very much. I will correct it. Election. You're right. Thank you so much.
So Q over M can be greater than 1. Little q.
I think we assume this is very small. Q over m is very small. Yeah. In reality, Q over m must be very small.
Well, it doesn't work for the electron, right? Well,
It doesn't work for electron.
or does it?
That's true. That's true. That's true. It doesn't. It doesn't work for electron. You're right. You're right. What's going on here?
Maybe there are some more constants missing.
Yeah, I think something missing. Something missing. Maybe let me open the tongues and what's they talking about? Good question. This is a good question. You're right. You're right.
If Q or M is greater than 1, let's say, it will affect the last term of the effective potential. So this term will dominate.
Yeah.
So
Which is not good. Which is not.
I mean, at first it was Q squared or R squared was with negative positive sign, but
Yeah.
it's negative.
So then it becomes negative. So there's no repulsion. That's which is not good.
Oh, in this particular equation does not depend on whether the small q and large q have different signs or not, right? Because at least the last term doesn't.
That's true.
So it's kind of doesn't matter if the particle is attracting or repulsing from
Seems like that's the case.
That's weird.
That's true. So I don't know. It's for me. I don't know. So in Townsend paper, Q over M is less than 1. This one is less than 1. I don't know why. If you assume this one, this is okay.
Maybe because we're considering like a small. We're not considering a separate particle, but a small like piece of dust from this ball of dust.
Yeah.
And then small q over small m should be the same as big Q over big M, because it's the same matter.
Yeah. I think that's
and that's less than
that's somehow estimated. This is equal to Q over capital M.
Small part of this can be a proton.
Anyway, somehow, yeah.
But it can be electron also.
But I guess we're just considering a small piece of dust.
Yeah.
It's very small. Like
So the ratio is the same somehow. So if you assume this one, actually Townsend paper actually assume this one.
If it keeps the epsilon very small, it's also okay.
Yeah, but here is most important one.
I think epsilon can't be like anything we want. The epsilon is.
Anyway, so in the lecture note, I will correct the lecture note. So this is assumption.
Oh, and one last question.
Yes.
If we were not to neglect the like axial movement, we would just get the usual term in the effective potential, something like L squared over R squared, just like in Newton's problem.
Yes. You're right. I mean, I assumed that I already erased L equal to 0, but we can do the computation and then do the computation and you get the L squared. You're right. Fine. So this is called the extremal case. Extremal. So this is the charge equal mass, so which means the electrical repulsion is equal to the gravitational attraction. Roughly speaking, in this case. And then, so the metric become like this way. So the two roots coincide inside for F, and then so therefore so the R plus is equal to R minus, which is equal to M. Okay, and then we can just do the computation as before. Introduce the torus coordinate, which is the dr over. I mean, it's just a repetition. I mean, square and then just solve it. R star is equal to R plus 2M natural log of R over M minus 1 and minus M squared R minus M squared IM and so on. So okay. And then if you write down the again the same exercise, B is equal to T plus R star, and u is equal to t minus r star. Then write down the metric in terms of u and v. I'm not gonna do that, but anyway, ds squared is equal to minus 1 minus, how to say, m over r square dv. Du dv plus r square d omega 2 square and so on. So unfortunately my lecture is not finished yet around this point. And this one again, if you introduce capital U, capital V, and then e to the r, what was that? U over 2m. And then this is e to b over 2m. Sorry, there's a minus sign here. And this is some compound factor of r, d capital U dv plus r squared d omega 2 squared, and whatever omega is. And this is non-singular at r is equal to r plus or n. So that you can just extend the coordinate to the r is less than m, and what's going to happen is as follows. So the component diagram becomes like this way. Like this way. And then horizon is always something like this is r equal to 0, so therefore here is it's just it's not horizon, sorry, singularity is here, and r is equal to m, r is equal to m, and r equal to m, so this yellow part becomes the horizon. So those are the coastal structure of the extremal case. Okay, so that's the case. And then one interesting for extremal case is as follows. If you look at so there is something called near horizon geometry. So if you look at the near horizon, so around here, how does sorry, I shouldn't use this one. Maybe I should use this shitty choke so around here. So if you want, the near horizon is around here. Okay. And we want to look at the metric around here. So it's a simple exercise to do. And then so to do that, you just introduce the notion r equal to m, close to m, and it's just perturb and rho inverse. If you do a change of metric around here, and the rho is very small, we treat it as a rho. Rho inverse is very small. Rho inverse is very small. Then the metric becomes like this: ds is equal to rho minus 2 minus dt squared. So I just do plug this one into here and do the manipulation. It's very straightforward. Minus dt squared plus and m squared and d omega 2 squared. And if you look at this one, so this is in fact is called this one. I will talk about the anti-Rosetta space 2. So this is a metric for ADS2. So anti-Rosetta space I will introduce later, but somehow magically it looks like ADS2, and this is S2. Okay. So near horizon geometry becomes ADS2 cross S2. So that's the nature of this extremal black hole. And this plays very, very, very important role in string theory. Actually, this extremal black hole, you can just add somehow fermions and so on in the space-time. So you can make it super symmetrized the space-time and make it supersymmetric. And in fact, the m is greater than or equal to q. So this is a physical solution we look at. It's called so-called BPS bound. So this mass of black hole is greater than the charges or equal to charges. It's called BPS bound, and this equality is called the BPS bound saturated is called supersonic black hole. And in fact, this extremal black hole will appear as a supersonic black hole in string theory. And if you look at the near horizon geometry, you get again it is 2 cross. In 4 dimension, it is 2 cross S2. In higher dimension, it is 2 cross some factor and so on. So always this is a very universal feature in the extreme black hole in string theory, and it plays very important role in string theory. But I'm not going to go into the detail. And then anyway, so somehow this extreme black hole is stable under some kind of deformation in the theory, so that it's easy to look at some stronger coupling regime for this extreme black hole and to see that some kind of like a quantum nature. Anyway, so those are like as you might heard of it, like a Strominger buffer or it is CFT correspondence. This is closely related to this geometry. Okay, I think it's a good time to stop, I guess. And yeah, okay. Let me take the again boat. Do you want me to talk, give a lecture about the gravitational redshift and then how to say precession of Mercury and also what was that? Deflection of light next week? Please raise your hand if you want me to talk about it. Let me count. Please let me count. I want to be democratic. 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, 9. If you don't want me to talk about next week, please raise your hand. 1, 2, 3, 4, 5, 6, 7. Okay, it's too democratic.
Can you tell us how to derive the quantum black hole?
So, current black hole derivation.
Yeah.
Derivation, I can write in the lecture note, but I don't want to talk about in the lecture. It's going to be a horrendous calculation. It's a really horrendous calculation. I can write the lecture note. I don't want to, but I can talk about the derivation. Okay, that's fine. But I don't want to spend it. I mean, it's just write down all the calculations and the horrible calculation in the middle. But that's all the audience will get lost interest. And I think that's I want to avoid. Okay. I'll think about the topic next week by myself.